both advocates for so, like,
This is Intermission trivia. Okay. You want to play one team or you want your own? Okay. There's prizes at the front that you can win.
He's looking for a little
great prize.
a little squeeze ball.
Yeah, I really think so. Okay. Or a chip.
We paid like $2,000 to $3,000 just for them to go to the doctor and
she went in, the symptoms were so and then when the scan came back, okay, no, actually, it's not within the site. Yeah, so it's just the exam, it's super early.
that's good. Almost the same thing. That one I had. So I got number one. Well, the appendix was taken up when I was working for TV, so I didn't have to pay.
Timed out. Yeah, it's
Now, technically, the money coming out of my pay, but they usually have
2009.
We'll start collecting some money advice.
I checked. As soon as I'd be able to take it out.
Seems like the volume's working all right on these. We're still going to take about a minute or two before we're going to get going. Welcome to Astronomy on Tap Charlottesville. I'll be your MC. In a couple of minutes, I'll get back on the mic where we're going to start our event. So take a couple minutes, keep chatting amongst yourselves before we get going, while my wife passes some stuff out for those of you guys that want to do trivia for tonight.
They asked how I wanted to play marathon.
Hey, will you bring that? Maybe you better.
I think we're going to go ahead and get started for tonight. Jennifer, if you don't mind, get the volume or the music in the back. Thank you. All right, guys, welcome to Astronomy on Tap. Welcome to Firefly, first off. Welcome to our Astronomy on Tap Charlottesville event. You guys might be wondering, why is there a grown man dressed up as Buzz Lightyear in the front of the room? It's because we're not going to take ourselves too seriously at Astronomy on Tap Charlottesville. We're going to teach you a lot about astronomy, have some fun trivia, some prizes, some really awesome astronomy talks. We're going to have fun, hopefully, the entire time doing that. I think coming to events, engaging with your community, engaging in science is one of the more meaningful things we can do as the conscious star stuff that we are, right? So I thank you guys for coming to these events. I hope you continue to come to more as the months go on, and I hope you have a good, fun time today. We've got a really fun event for you guys tonight. So my name's Matt Pryal, or some of you may know me as Matt Pryal. You may know me as an assistant professor of astronomy in the Department of Astronomy at UVA. But for those of you in the AOTCville family, you know me as my true self, who I really am when I put on the costume. I am Professor Buzz Lightyear, getting slowly more buzzed as the night goes on. And I'm here to lead you guys through the fun trivia and talks that we have tonight. Got two awesome speakers, both by experts in astronomy in the UVA Astronomy Department. Sahana and Daphne are going to be talking about a little about their research that they do as graduate students and postdocs in the UVA Astronomy Department. So, for those of you guys that are new to the AOTCville family, first, welcome. You are now a part of the family. We've been having these AOTCville events since 2018. So back when I was a graduate student in the astronomy department at UVA. Me and my good friend Trey Wenger. Trey Wenger started the Astronomy on Tap Charlottesville events. He quickly had to defend his thesis. I took over as a graduate student, tricked the UVA Astronomy Department into hiring me as faculty, and was able to continue on from then on. But we've had 33 events over the years, going to a bunch of different bars, and have found a little home at Firefly for the past couple of events that has been really great to us. Astronomy on Tap itself is an organization that's been going for 10 plus years, that was started by some astronomers in New York, and there's been a bunch of satellites that have branched off and sort of done their own thing as the years have gone on. All right, so what are the schedule looking like for tonight? Well, we're going to start off like we typically do when we got two speakers with some fun group family trivia going on. I'll get to that in a moment. We are going to be deciding between Earth and the solar system in our team trivia game. Then we're going to dive into our first talk of the night. Sahana's going to be talking about her research on exploding stars and other things that go bump in the night. Then we're going to have some more trivia, some intermission, get more drinks. I'm going to be setting up my binoculars, maybe after the event, so that we can look at the moon, and they're like giant binoculars, just so you guys can see. This is how big the binoculars are. It's effectively just a telescope that are binoculars. My family got them for me for one Christmas. And then we're going to be diving back into some more trivia before Daphne's going to be talking about her research about exoplanets, planets outside of our solar system that we've started to learn about over the past 30 or so years. All right? I want to remind people as well that Astronomy on Tap, these events are free. We love putting them on for you guys. But all the trivia and the prizes that we have and that we're going to be giving away, we're only able to do so if you guys are able and willing to donate some money for the events that we're able to put on. So I appreciate we have a little fun with those donations. You guys are going to be deciding between your favorite. You'll understand the pun hopefully in a couple of talks. We're going to be deciding between soup or Nova. Soup or Nova, whatever your favorite is, you guys can throw some money at the front, whether you like soup or Nova a little bit better. All right. I also want to remind people about some fun astronomy events that are coming up. If you've never gone to a McCormick Public Night at McCormick Observatory, they're held every first and third Friday month for free at the McCormick Observatory. You need a ticket to get to them, but they're free. I encourage you guys to check those out if you've never been to an event. There's a star party. Dark Skies, Bright Kids is an awesome outreach organization that is run by graduate students primarily at UVA. They're hosting, again, a free star party this upcoming September 20th at Admiral Cider Works. Have telescope observing, constellation tours, kids activities, some food trucks, planetarium shows. Really great event to go to. It's an event that I used to run back when I was a graduate student as well. Our next Astronomy on Tap event is going to be on November 3rd. It's the first Monday of every odd-numbered month, specifically when we have our events. And then there's a lot of events coming up by the Charlottesville Astronomical Society. So just give a plug to CAS, the Charlottesville Astronomical Society. They run a lot of great observing events throughout the area. If you're into looking through telescopes, which you should be, it's awesome to look through a telescope. If you've never seen Saturn for the first time, or for the first time through a telescope, it's something you absolutely have to do. CAS puts on a lot of those events around the community. I encourage you guys to reach out to them. All right, so with that in mind, we are going to segue then into our first team trivia event or activity for the night. This does not make use of these sheets that you have in front of you. We're going to save those for the main trivia halfway through the night. Our team trivia is going to be decided to determine whether you guys are going to be able to get some of these mini prizes in the front of the room. And we're going to be doing Earth versus the solar system. Alright, so the way that Earth versus the solar system is going to work is that you guys, surely you've done all your research, you've done your homework, you know the solar system inside and out, you've lived in the solar system your whole life, right? You guys are intimate members of the solar system, know everything about it. You're going to decide with the consultation of those around you, and I want you guys to get to know the random people that are next to you. Again, it's part of the best parts of these events, getting to know your community members. Whether the answer to the question is the Earth or the solar system, and you're going to decide by voting which of those two answers you think is correct. If you guys get more questions right than wrong, you win these mini prizes up the front. And those of you guys that have been to these events know that whether you get them more right or wrong, you get the prizes regardless. It's just a lot more fun for us if you guys get more right than wrong. So, how is this going to work? As an example, let's imagine I pose the question, what has more beer, the Earth or the solar system? Chat amongst yourselves for 30 seconds to decide which of those two you guys think has more beer. And I'm doing my part to make less and less beer on the Earth.
You want to join us? Are we doing the best we can? We all win. Yes, exactly. We're going
All right, consultation's up. We don't want people chatting too much with each other. Just by a round of applause, who here thinks the answer to this one is the Earth? And who here thinks that it's any other object in the solar system? No, I don't think so. We're hogging all the beer on the Earth. That would be absolutely correct. The rest of the solar system has no beer. The Earth has at least one beer, but it's having less and less beer as the night goes on here. It's going to get a little bit more challenging. We got 7 questions, which means you guys got to get at least 4 of them right. So first question, getting a little bit tricky. Which is the densest? The Earth or any other object in the solar system? And we're going average density here. What is the densest? Chat with your neighbors about this one. I'll give you guys like 30 seconds to a minute of chatting about this.
That's the galaxy, not the solar system.
And they're feeding
So the question here is, it has to do with density. Is it average density of the whole solar system or just any object? It's any object in the solar system. Is there any object in the solar system that's denser than the Earth? Alright, I've given you guys enough time to chat though. Again, by a round of applause, who here thinks the answer to this one is the Earth? Couple people sticking with it, nice, like it. Members of cast. Who here thinks that this is any other planet or moon in the solar system? Nice, we have a consensus, so clearly the answer must be this. Wrong. You guys would be incorrect. It is the Earth on this one, believe it or not. Sometimes it's exciting to stick to your convictions, even if the whole group doesn't think so. The Earth is a little denser than effectively every other object in the solar system. What's the next densest object? Mercury, a little less dense than the Earth. The densest of the gas giant planets, Neptune, is almost the density of water, and the densest moon, Io, around Jupiter, is nowhere close to the density of the Earth. The Earth's the biggest rock in the solar system. It's also the densest object in the solar system. You guys are over 1. Alright, so we got to get a little bit better than that. Which is greater? The number of Americans with the last name of Moon, such as football star Warren Moon, or the number of moons in the solar system? Which of those two is greater? I'll give you guys about 30 seconds to chat with your neighbors about this one.
So I'm seeing the number. There are a lot of them. There are a lot of
We had a question about the definition of American here. If they were in the census, the U.S. Census is what I'm getting at for this one. All right, keep chatting amongst yourselves for this. All right, time's up for this one. Let's see what you guys think. You guys are over 180 to redeem yourself. Who here thinks the answer to this one is the number of Americans with the surname of Moon? All right, what about the number of known moons in the solar system? Oh, I did not say that. We'll just say number of moons in the solar system then. Because it's not going to matter for this. The answer to this one is absolutely the Earth, whether it is the known moons or the unknown moons. So there's about 65,000 known moons that are Americans, about 758 known moons in the solar system. All right, you guys are 1 for 1. That means you got to get 3 more right to get the prizes. Next question, question 3. What has the most fire? We're talking about fire by total energy at any given time. Is it the Earth or any other object in the solar system? I'll give you guys about 30 seconds or so for this one. What has the most fire?
I think a fire.
We're not talking about temperature. We're talking about, well, I guess you could ask.
Question in the back, right there. Keep chatting.
What about the sun?
I was thinking.
The sun's got a lot of.
The sun is absolutely in the solar system, so the sun would count, but I'm thinking if it's on fire.
Okay, so I'm thinking fire is like a combustible reaction.
Yep, that's right. Because fusion is not fire, so that's a key thing for the sun. The sun is not the right answer for this one. I'm not going to say if there's another object. Right, let's see what we think here. So who here thinks the answer to this one is the Earth? What about any other solar system object? I think I'm giving that one to any other solar system object. It was close, which means those of you guys that choose the Earth have to be a little bit louder next time if you're more confident in the answer. There is no other object in the whole solar system that has fire. You need oxygen to have fire. The Earth is the only place. Oh, don't give me that. That's Professor Buzz Lightyear to all of you guys. No, the Earth's the only place that has some fire. Nowhere else in the whole solar system has fire. The sun is not on fire. Io is not on fire, right? The Earth is the only object in the whole solar system that has fire, which is pretty cool. That's why we're here, right? Because the Earth is capable of having fire. All right, you're 1 for 2. Next question, which is faster? The speed that the continents move on Earth or the speed that Pluto moves around the sun? I'll give you guys about 30 seconds for this one.
Tectonic plates for
All right, time's up here. Who here thinks the answer to this one is the speed that continents move on the Earth? What about the speed that Pluto moves around the sun? You guys, the consensus is Pluto on this one, and that would be correct. In fact, it's not actually close to this one. Pluto is the slowest moving object of the major planets in the solar system, right? But it's still moving about 10,000 miles per hour. The continents move only a couple of inches per year. Fun fact, it's about the same rate that your fingernails grow, if you're curious about that. All right, you're 2 for 2. Question 5, you need 2 more right. Which has a greater volume? The Earth or the volume, total volume of every known moon in the solar system combined? What has a greater volume? I'll give you guys like 30 seconds for this one. Alright, time's up here. Who here thinks the answer to this one is the Earth? One couple people. What about every known moon in the solar system combined? Alright, I'm giving that one to the moons, and unfortunately, the answer to this one is the Earth. What's the volume of the Earth? It's 1 Earth volume. What's the volume of all those 760 moons? It's only about 0.3 Earth volumes. The moons are really tiny. It's why they're moons, right? The Earth, again, is the largest rock in the solar system. It's much larger than all of the other moons combined. All right? Means you guys got to get the next 2 right to get the mini prizes. You're getting them regardless. It's more fun if you get them right than wrong. All right. What is the most reflective? Is it the Earth or any other solar system planet? Which one is the most reflective? And I'll give you guys, and that includes their atmospheres. I'll give you guys about 30 seconds for this one.
Okay, sir. I'm not sure what it is. Venus or maybe one of the ice It's only 0.39.
All right, let's see what you guys are thinking here. Who here thinks the answer to this one is the Earth? What about any other solar system planet? Nice. I'm giving that one to any other solar system planet, which would be correct on this one. Venus is the most reflective of any of the planets. Its thick atmosphere reflects almost 70% of the light that impacts it. If not for its carbon dioxide-rich atmosphere, Venus would actually be incredibly cold because of how much light it reflects. But its carbon dioxide atmosphere holds all the heat, the majority of the heat that actually gets in there. You guys, it's coming down to the last one. You guys are 3 for 3. Final question, which object, oh yeah, let's go, a little drum roll for this one, I like that. What object is the most spherical? Is it the Earth or any other solar system planet? Now what do I mean by that? Imagine you had a pizza dough, you started as a sphere and you started spinning it. As you spin it, it becomes less spherical, right? So we're talking about how much this diameter differs from this diameter. The one that's closest to being the same is the most spherical. So what object's the most spherical? The Earth or any other solar system planet? I'll give you guys like 30 seconds for this one.
The Earth tends to actually expand and contract. Not have
most spherical? Do we think that it is the Earth? You got that, Dr. Yes. What about any other solar system planet? Alright, it's a good thing her hands are full, because we're giving it to any other solar system planet, and any other solar system planet is the right answer here. In fact, it's Venus again. Venus is effectively the most spherical object. Why is that? Because Venus spins incredibly slow. It spins once every 240 days. Earth is not a perfect sphere. In fact, Mount Everest is not the farthest that you can get away from the center of the Earth, even though it's the tallest mountain. There are mountains that are on the equator that are technically farther from the center of the Earth because the Earth bulges a little bit due to its rotation. All right, that means you guys got 4 out of 3 right. During intermission, I'm going to call you guys up to the front. Everybody's going to be able to come up to the front, grab some of these mini prizes. So round of applause, you guys, as we're getting more right than wrong. All right. Then what we're going to do is we're going to transition to our first speaker of the night. So our first speaker is going to be Sahana Kumar. She's a postdoc at UVA in the UVA Astronomy Department. She's going by Sahana Lose some volume. No, we're good. She's going by Sahana the Supernova Hunter tonight. She's an observer who uses telescopes all around the world to study supernovae, which are the explosive deaths of stars. Seems like we're having some audio issues, which means you guys, oh no?
I was just lowering this one.
Oh, okay. You guys are okay over there? Okay. That means it's still going to take me about 30 seconds or so to get Sahana's talk set up, so I'll give her a round of applause as she comes up. Okay, let's give another round of applause for Sahana for the talk.
Alright, hi everybody. My name is Sahana. Happy to see some familiar faces in the crowd tonight. So, press the button. Alright, we're good. So as Matt said, I am a postdoctoral researcher in the UVA Astronomy Department, and today I'm going to take you on a little trip through what I do on a daily basis, which is search for exploding stars out in the universe. By the way, we are going to have questions at the end, but feel free to pause and shout out a question in between, but I do reserve the right to say I'll talk about that a little bit later. So feel free to ask questions if they come up. And let's get going. So, there we go. So I study a range of objects that are called astrophysical transients. So astrophysical transients are actually a pretty broad category and encompass a lot of the really cool things in outer space. But for today, the thing I want you to keep in mind is that these are things that change quickly. And more importantly, they change fast enough for us to observe as humans. Oops, wrong button. So when I say change, there are various ways that astronomical objects can change. So one, they could change their position on the sky during the night. They could be getting brighter or fainter. There could be something that looks like it's changing its size, or we can see something pop up entirely new where there seems to be absolutely nothing at all. So these are the kind of things that I look out for on a daily basis. The time scale is also really, really important. Us as humans, we live very, very, very short lives compared to most of the things in outer space. So for us to be able to study change, we're kind of restricted to things that change fast enough that we can follow them during our limited lifetimes. So we typically split these up into a couple of categories. There are very fast or very rapid astrophysical transients, so these are things that are changing over the course of seconds even to hours. Then we've got slightly more moderate transients, so these are things that are changing over the course of days to weeks. And then we have more longer term transients that change over the course of years. So even if something is changing over the course of like 50 to 100 years, that's a pretty long time for us humans, but in astronomy terms, we still consider that a transient, and it's changing much faster than things like galaxies or planets that take millions and millions of years to evolve. So we're looking for things that change, and more importantly, change fast. So like I said, astrophysical transients is actually a pretty huge umbrella term and incorporates a lot of cool stuff that you've probably heard about. So some of the most common astrophysical transients that we see here at home on Earth include comets and asteroids that fly through our solar system. So this is an example of an astrophysical transient that changes location, and that's how we track them each night. We also have good things like planets and moons. I can see here this is a very astro-leaning crowd, so I'm sure many of you are familiar that the name for planets comes from an ancient word for wanderer, because these things were changing their positions over the course over time, and people were noticing as they were looking up at night. Same with the moon. Our moon itself is an astrophysical transient. When I'm using telescopes, I gotta figure out where the moon is, because it's somewhere else, basically, each night. So we consider it a transient as well. When we get outside of our solar system, outside of our local neighborhood, we get some real crazy stuff. This includes variable stars. So I'm not going to go into these today, but they're super cool. They're stars that basically puff up and then scrunch down, puff up and scrunch down over the course of their life. So that's an example of a transient that changes its brightness over time. We've got pulsars, which if you come to AOT, we've got actually a real great pulsar community here in Charlottesville through NRAO and UVA. Yeah, we got the pulsar folks here. These are also a form of astrophysical transient, and there are things called millisecond pulsars that are very important for research, and so these are things that change in less than a second. So we're dealing with all sorts of timescales here. Then we've got even more exotic phenomena like tidal disruption events. So this is a situation where a black hole will basically eat a nearby star. And so this is a situation where we'd see a star one day, and then you look the next day and that star is gone. It's been eaten. These things are super cool, but they're not actually what I study. What I study are supernovae. So let's get into those. So at a base level, supernovae are the explosive deaths of stars. All kinds of stars meet the end of their lifetimes in these cataclysmic explosions, and that's what I study here at UVA. So there are two main categories when we're talking about stars exploding at the end of their life. And these categories are actually based on that star itself. So on the one hand, we've got smaller stars. And when I say smaller stars, I mean stars that are actually kind of the size of our sun. So our sun is a pretty average star, and it falls kind of on the smaller range of stars. So small stars, they tend to explode. Smaller stars, they explode via what we call thermonuclear runaway. They become unstable, and they deal with the same sort of physics that's actually in an atomic bomb. So they will explode. But on the other hand, even more massive stars also explode, but they explode in a slightly different way. Just real quick, stars are like burning balls of gas, and once they run out of gas, just like your car, it's going to stop once the fuel tank is empty. Same with our stars. Once your fuel tank's done, it stops putting out energy, and it can no longer withstand collapse against gravity. So astronomers have been looking at these exploding stars for many, many years, and we've put them into two categories based on how they explode. And after many years of doing this, they came up with the wonderful names of type 1 and type 2. And yes, that is still the classification we use today. So type 1s are the small ones that explode like an atomic bomb. And then type 2s are the larger ones that just can't hold up their own against gravity anymore and collapse. So both of these result in explosions that we can see with our telescopes from here on Earth. So let's take a look at what a supernova looks like. Matt, would you mind playing the video? Thank you. So what we see here is a bright spark that gets brighter over the course of about 20 days and then will fade over time. Let's play it one more time. Thank you. So as you can see, this right here is what we call a light curve. This plots the brightness of the object over time, and all supernovae tend to show this same structure, where they'll start nice and faint, they'll get really, really bright, and then over the course of a few weeks, they'll fade away again. So this is one thing that we look at with our telescopes, is we try to make a light curve by looking at them each night, and we'll construct the light curve. And that's one way that we can figure out what sort of astronomical transient are we looking at. So the other thing to know about supernovae is they are incredibly bright. There are a lot of bright things out there in space, but these are truly some of the brightest. And when I say they are bright, They're typically the explosion of, we think, a single star. And when they explode, they can outshine their entire host galaxy. Galaxies are made of hundreds of millions of stars, and a single one exploding can outshine all the rest. If we were to make an analogy to what that would be like for something in our everyday life, this would be equivalent to a single light bulb, this guy right here, outshining every single other light on the continent of North America. Not just the US, but the entire continent. So these things are extremely bright. And that's actually really good for people like me who are looking in the vast darkness of space trying to find them. So we look for these bright flares, essentially, that pop up. And if we see something that is unusually bright, that's when I get excited and start going after it. So these things get insanely bright. And astronomers actually learned this lesson kind of in a hard way. So in this photo here, this is a now famous photo that was taken by the Hubble Space Telescope about about 4 years after it was launched. This right here is a very famous supernovae called 1994D. The way that we name supernovae is literally the year that it was found, and then we just go alphabetically over the course of the year as we keep finding new ones. So this one was found pretty early in 1994, but the way they found it was kind of crazy because this supernovae almost actually broke the entire Hubble Space Telescope. There was a different program that was looking at the host galaxy here. They were trying to do some science with all the cool stuff happening in the galaxy there, but there was a single star in the outskirts that happened to explode at the time Hubble was pointing it, and they had to do evasive maneuvers to make sure it didn't blow out the entire detector. So, space telescope people get a little nervous about these explosions, but I love them. And what's great about them is because they're so bright, we can use them to reach farther than we can with some of the other techniques that we use. So just like here on Earth, when you're lost out at sea, sailors rely on lighthouses to figure out how far away are you from land and how close are you to the shoreline. We do something very similar with supernovae. These act as cosmic lighthouses because we know we have a very good idea about what type of star explodes. We can figure out how bright it needs to be. And then comparing how bright we know that star should be to how bright it is, just like how a fainter lighthouse is the further away it is from you, we can use these stellar explosions as cosmic lighthouses. When I taught a lot of undergraduate classes, my go-to analogy was a city skyline. The universe is like a city skyline. As you're driving up towards the city, you see all the big, beautiful buildings standing next to each other, but from far away, you cannot tell how the streets and blocks are offset from each other. You need things like lights in the windows to tell you how far away those buildings are. So just like that, supernovae are lights in the windows that tell us how far these different galaxies are. And supernovae, type 1a supernovae, actually led to the 2011 Nobel Prize in Physics, which showed that the expansion of our universe is accelerating. So we really need these cosmic lighthouses to figure out how big the universe is. It's big. So, supernovae are not only important just because they're really, really bright, and let's be real, exploding stars are cool, but we also need them for some very important science reasons. And that has to do with the chemical composition of our universe. So stars are the birthplace of a lot of the elements that we rely upon, but there is a physical limit. Stars cannot generate elements heavier than iron, thanks to lots of fun stuff with atomic physics. So if we need to fill out the rest of the periodic table, literally all of the rows except for like the first one, we need something else. And that something else is exploding stars. So the analogy that I like to make for this is if stars are an oven, you can bake a lot of things in an oven. But ovens have a limit. They can only go up usually to like 500 degrees Fahrenheit. But sometimes you need some more heat. You need that extra crunch. You need a deep fryer. Supernovae are the deep fryer. All right? This is how we get even higher temperatures, higher density, just really, really intense conditions that are needed to force atoms together and fuse and create different elements. So I wasn't kidding when I said we really need them. If we take a look at the chemical composition of our universe, and we take a look at where those elements are produced, the vast majority of elements that are required for the building blocks of our human bodies come from exploding stars. So this is also one way that we have figured out the generations of stars, or where we as humans are in the cosmological timescale. We know that there had to have been at least one generation of stars that exploded prior to us that leads to some of the heavier elements that are in our bodies. So we know that at least one round of stars exploded prior to us coming here, and we need them to continue moving forward. So they are a very, very important mechanism for producing elements and spreading those elements within their host galaxies. So, now that I've gone through all the reasons of why we want to look at these supernovae, let's talk about how we actually study them nowadays. So, the main way that we find them is through a technique called difference imaging. It's basically spot the difference. So we scan the sky each night, and we're basically looking for new point sources or new spots of light to pop up in our data. This is an example of one of my favorite supernovae, 2011 FE. What we see here is, you see this little green arrow right here, it's pointing to the location of the supernovae. These images that I'm showing were taken over the course of 3 nights, and you can see, even just over the course of 48 hours, we go from there looking like there's absolutely nothing there to clearly a very bright spot. So one of the early ways that we did this was literally every single night just looking for something there. Astronomers have been doing this for well over 100 years now. This is a historical example. For those of you who are familiar with Edwin Hubble, he's a very famous astronomer, also the namesake of the Hubble Space Telescope. This is one of his more famous photographic plates. This was back before we could use essentially digital photos, where they physically put glass plates at the top of the telescope. And even within those glass plates, he noticed that there was a new dot over the course of each night, and circled it and wrote VAR, like variable. And I got to see this plate in person during my last year of grad school, and it was honestly a pretty great nerd moment. They have it at Carnegie Observatories in Pasadena if you ever want to go see it. It's pretty cool. Since Hubble's time, we now don't have to use photographic plates. We've come a long way. We've come a long way. Now we actually rely on networks of robotic telescopes. So this is the primary way in which we track the sky each night, and more importantly, are able to get continuous monitoring of the night sky. So this is an example of the Las Cumbres Observatory. This is a telescope network that we at UVA use very almost daily at this point to study supernovae. And it's a network of robotic telescopes located all over the world. They operate completely independently. They point to the sky, scan the sky each night, and send us the data each morning, and we look through them to look for new objects. There are now multiple telescope networks like this that are covered around the world, and we've got like pretty much all sky coverage from the ground at this point. And as you may notice, we've got sites in both the eastern and western hemisphere, and the northern and the southern hemisphere. So one other really, really fun thing about being a supernova hunter in this day and age is I get to be part of an international team. We basically relay race around the world. Whenever the sun's coming up, you pass it on to the next team. So it's also really fun to be part of this, essentially relay team where we race the sun and we win. Astronomers, sorry, I pressed the power button. Hello? Okay, I'm back. So, some of you may have heard astronomy, especially transient astronomy, has entered a new domain as of a few months ago. We now have access to the largest camera human beings have ever built. And when I say this is a large camera, the statistic that really blew my mind is, have you all heard about the Sphere in Las Vegas? That big like dome thing that's like massive? One image, just one picture from that camera, the dome can only display 1/5 of it. Yeah, 1/5. You need 5 spheres to see one LSST image. It's that big. And if you're going to use super high definition TVs, like a large flat screen TV, you're going to need at least 400 to see one image if you have a 1:1 pixel scaling. So huge camera, which is awesome. It's located in Chile on an 8.4 meter telescope and just started science operations earlier this summer, back in June. So we're now entered the LSST era. This is again another automated telescope that scans the sky each night. But now that we've got the biggest camera human beings have ever built, that leads to a new problem that astronomers get to deal with, which is a lot of data. And this camera is generating approximately 20 terabytes of data per night. If you buy a brand new laptop nowadays, usually they'll come with like 1 terabyte. So one telescope that we have is filling up 20 laptops a night. We've got a lot of telescopes. We've got a lot of data. So astronomy is actually one of the forefronts for dealing with big data. Yeah. Fantastic question. So actually data center, yeah. So the question was, where are we storing all this data? So that is a huge part of it. So for LSST, they've actually built dedicated data centers. So there's one hub in Chile and then 2 larger hubs, one hosted at Stanford by SLAC, and then the University of Washington is another big hub for LSST. Yeah. So lots of data infrastructure to deal with all of this. And so we have to employ some use. But before we get to that, let's just take a sec to look at this beautiful image. So this here is actually one LSST image of the Virgo cluster. And fun fact, so this was a single snapshot image that they took and they released in just one image snapshot look of something in our neighborhood. They found 6 supernovae. Yeah, and there's only getting more. So these things we're finding out are more and more common the more that we look. There are a lot of stars exploding out there, and with LSST we're going to get to see many more of them. So back to this conundrum we have now of just a fire hose of data coming at us every single night. How do we keep up with it? So we rely on things that are called transient brokers. So these are essentially pieces of software that go through this massive data stream and try to help us pick out the objects that are scientifically interesting for us. So this is one area that astronomy is really leading efforts in, specifically machine learning and applications of AI to sort through these large data sets. But of course, this still requires input from human astronomers, because one of the cool things about space is that there's a lot of stuff out there we don't know about. So these have also been a cool way of doing anomaly detection or finding unusual things in our data stream so we can go look at them with other telescopes. So there's a lot of efforts being put in how do we utilize modern technologies that come from other aspects of our life and use them to help our data stream and help inform the science that we get from these objects. So now that I've told you about a little bit about how we find all this stuff, I do have a question for you. Now that we've had humans and the machines racing for a little while, who do you think finds the best supernovae? I'll use Matt's system here. So first, applaud if you think it's human astronomers who are still in the lead. Coming out strong for the humans tonight, love to see it. How about the AI? Who thinks the AI has got the edge on us? Alright, we got a couple folks who have some faith in the machines. Sorry, it was a trick question. Actually, the answer is neither. The answer is the public, the community. So I wanted to highlight some of the other ways that we find astronomical transients, not just from our robotic telescopes, because remember, these are only located at certain places around the Earth. A huge part of astronomical discovery or transient discovery actually comes from the community and citizen scientists. And part of this has to do with the fact that the night sky is part of your home. It is the ceiling under which we live under. And if you've lived in your home for a really long time, you can always tell when something's a little off. It's like when you come home and someone's moved something. You know something is off. There have been so many supernovae that have been identified by eye, by just normal people looking up out their backyards and seeing something new and telling an astronomer about them. This includes people like kids. We have a number of kids who have discovered supernovae. And the cool thing about the supernova community is if you discover a supernova, you get credit for it, regardless of who you are. You will get credit for it. We make it what's called an astronomical telegram. And yeah, we're just happy to have people involved. So a lot of school kids get involved with this. There's cool community efforts run through local astronomical societies and also just groups of astronomy enthusiasts. One group that I've worked with in the past and have enjoyed meeting is BOSS. This is a community survey based out of Australia, and it's a bunch of barbecue dads. They literally just get together, they barbecue, they put their telescopes up, and then they call us the next morning and they're like, hey, we found some stuff. We had a great time, but we also found some stuff. And it's great. We also have Itagaki-san. Oh, his name got cut off a little bit. He is another person who was in the supernova community, loved. He is a retired businessman in Japan who, in his retirement years, got very interested in astronomy, set up a little telescope in his backyard, and in the mornings, while drinking his tea, he looks through the data stream, and this guy catches so many supernovae. He has beat Hubble and James Webb's telescope multiple times, and being located in Japan, he's also at a location in the Earth where, we get this vast nighttime over the Pacific Ocean. So he helps us catch things that astronomers on the west coast of the US or Hawaii might have missed. And he is a very prolific supernova finder. We think he's probably the most prolific supernova hunter alive today. So actually a lot of really important contributions to our field comes from the community and citizen scientists. So I wanted to wrap up today with a couple of options or a couple of ideas on how you might be able to incorporate transient astronomy in your life, because we could definitely use your help. So one way has to do with this new mobile game that was put together by a software group at Caltech who also does supernovae, and it's basically like Pokemon Go on your phone. This is based off of what's called the Zwicky Transient Facility. This is based in Southern California, so same hemisphere as us, and you can walk around at night. Maybe you're taking your dog out for a quick bathroom break, you're waiting for them to do their business, just point your phone out. And what we want to know is, do you see something different than what the telescope's feed sees? And they've gamified it. Definitely recommend checking it out. There is a QR code there. If you want to use that, that'll take you to the download page, or you can also just look up Zarth on Android and Apple iPhone store. There's another thing that came out actually very recently, and this has to do with LSST. So this is, again, the largest camera that human beings have ever built. Science operations have started, and with that, LSST is already making fantastic discoveries in multiple areas, not just supernovae. And they've launched 2 new interactive things that I would love to share with you. So one is called Orbit Viewer. It's basically, you get to fly around the solar system and it's like a 3D projection to get to see all of the new stuff that LSST has found in our solar system, as well as little flybys, and it pops up with this gorgeous little box explaining what's going on, and you can fly around. And what's cool is that they are updating this in real time with LSST discoveries. So if you log in tonight, and then you log in a week from now, there's probably going to be about 1,000 more objects than there were tonight. There's also this thing called Sky Viewer, where you can look at other galaxies. So you can look even further out. And this is where you can basically fly around that beautiful big image that I showed you earlier. And this observatory is named after the great Vera Rubin, who many of you might be familiar with, very foundational female astronomer who did some very important work specifically in discovering dark matter in the universe. And one thing that she looked at was nearby galaxies. So they recently put out this fantastic virtual tour of Vera Rubin's galaxies, where you get to fly into them in these high-resolution images. So I highly recommend you check them out. If you are an educator or somebody who works with kids or wants to give your own kids like a cool 15-minute activity, I highly recommend checking these out. And if any of you have a VR headset, please try it out and then come tell me about it at the next AOT, because I think that would be real fun. So with that, I wanted to say thank you all so much for coming today. That's it for me, and I'm ready for some questions.
All right, guys, we got some time for questions, and we got fancier for this AOT. We got 2 mics, so I don't have to keep running back and forth. And so we got a question up the front here.
So I keep hearing one of our near neighbors, Betelgeuse, is about to blow. What's the over-under on that, and what would it look like from Earth?
That's where we go. Yeah, so that's every supernova person's favorite question, because honestly, we're all hoping it explodes. It's going to be rough for us on Earth for a few days. It might, mess our electronics up a little bit, but we really want it to. Unfortunately, the over and under is like several 100,000 years. Yeah, so you may have heard like a couple years ago there was a great dimming event of Betelgeuse, and we were all just sitting there being like, go, do it, die, do it. It didn't happen.
Other question?
Yeah, over here, up the front. I'm still running around regardless of if I have 2 mics.
Hey, kind of plays off his question a little bit. If a nearby neighbor blows its top, say Alpha Centauri flips its lid tomorrow, how screwed are we here on Earth?
So we are lucky in that we do have some alert systems set up. So what's cool about supernovae, especially the core collapse ones, which we think something like Alpha Centauri might do, is that they will expel a string of high energy particles called neutrinos before the actual explosion happens. And here on Earth, we have a couple of neutrino detectors located all over the Earth. So what we're hoping for is that if a nearby neighbor is going to explode, we'll have hopefully a 48-hour heads up. Depending on how close it is, yes, it could cause some real problems. Primarily because these explosions, they unleash so much energy. They're some of the most energetic events in the universe. And for us here on Earth, primarily what it'll mess up has to do with our electronics and our telecommunications system. So I think a lot of our satellites will be messed up, might mess up some of our large-scale technology, but for the most part, we should be okay. We have systems in place for it. It will not physically blow us up, no. The closest star to us that will likely blow up is the sun, but it's going to take a real long time to do that. Yeah.
Other questions? Yep, I got you behind you. You're good.
Hello. So are supernovas, are supernovas powerful enough for gravity wave detectors like LIGO to also detect?
Yes, so some kind of supernovae, yes. So there are a couple of subtypes of supernovae. So I mentioned we have the type 1s and the type 2s, but each of those types actually have subtypes that are lettered. And so we do think that there are some subtypes that are when a star collapses to a neutron star or a black hole that could potentially create a gravitational wave. So we do have one example of this. This happened in August of 2017. There was a neutron star merger event that led to what was called a kilonova. So we actually find the gravitational wave events that we've discovered so far are associated with these sudden bright explosions, but it's not as bright as just a star exploding. So still just the explosion of a star is more bright from what we can see from here on Earth than something like a gravitational wave event. But that is actually something that LSST is working on because it has such a big field of view of using it as a way to try to catch and see if these explosions are bright. There is some wiggle room, we're not entirely sure because we've only had gravitational wave detectors for a few years. So I think that's something that, keep an eye on that space in the next 10 years. We might get some really cool new explosions.
All right, we got time for maybe one more question. We got any other questions with the group? Oh, you got one more right here? All right.
So, this is my brother, and he's the one who asked the question about Betelgeuse, and I want to know how he knew to ask that. What makes us think Betelgeuse is going to blow? Because he didn't tell me.
Yeah, so there are a couple of reasons why we think Betelgeuse is going to blow. So one, it is an evolved, I think it's a red supergiant, right? Stellar peeps? Yeah, red supergiant. So it's in one of the later stages of stellar evolution. It's reached essentially like the old age of stars. And so because it's in its last life stage, we're like, all right, we know supernova is next, just please happen already. And I think you were referring to, there was some excitement a few years ago where Betelgeuse did show some dimness, which is one of the precursor signs for a massive star exploding. Remember, like I said, the reason why they explode is because they've run out of fuel to offset gravitational collapse. So actually these massive stars go dark for a few hours right before we see the big explosion. So the fact that Betelgeuse started dimming made all of us go like, all right, it's happening, let's go. And then when it started getting brighter again, we're like, okay. Yeah, so I'd say it's mainly because it's in its late stages, and it started showing some activity that was like a precursor to it, and we all just got real excited. It didn't happen, but that's not going to stop us from getting excited next time too.
All right, well, let's give another big round of applause for Sahana for an awesome talk. All right, guys, so what we're going to be transitioning to next is our main trivia game for the night. So the way that this trivia is going to work is going to be by using these trivia sheets. You can either work on your own if you don't want to chat with the people next to you, or you can work as a team for this. We're going to be choosing a couple of people, the ones that get the most correct, and also some random people, including ones that didn't get a lot correct, to win some of these prizes at the front. If you need one of these trivia sheets, please just raise your hand. My wife will come around to be able to help you out. She's the one that's very, very short. Alright, so what I'm going to do is I'm going to scan through these questions. I'm going to read them for you guys so that you can get a sense of how the questions are working. And then we're going to start our intermission. I'm going to let the questions sort of flow for about 10-15 minutes. We're going to turn the music back on, give you guys some time to think, get some food and things like that, and turn those cards in. All right, so I'm going to come back to this in just a moment for those of you guys that want to scan the QR code for those questions. Our first question tonight, though, has to do with time. And specifically, which of the following terms involving time does not find its origin involving astronomical objects in the sky? Is it the month, AM and PM, the week, a minute, or a year? And I got some students that are here, so you guys should be getting this one right. Question number 2. A supernova can occur when a massive star collapses at the end of its life, with rebounding material making it one of the most energetic phenomena in an entire galaxy. Where does the origin of the name supernova come from? Is it part of the name of the first astronomer to document them? Is it a Roman military term? Or is it the appearance of a particularly bright new star? Is it inspired from a term used in Italian operas, which I will not recreate right now? Or is it a Greek mythological god? Question number 3. Which of the following names was never used or proposed as the name of a planet or large object in our solar system? Our last talk's going to be about planets, so we got some trivia questions about planets for you guys. Is it George's star, Vulcan, Make, Jason, or Juno? Question 4, which was our Facebook trivia hint. If you guys follow us on Facebook, you can get the answer to this question. You're still welcome to do that tonight, but no looking up any of the other answers. When was the first planet outside of our solar system discovered? Was it in the BC era, around 350 AD, in the early 1700s, around 1880 AD, or the early 1990s? Question number 5. Which of the following solar system planets has the longest day? Is it Mercury, Venus, Earth, Mars, or Jupiter? This is a were you paying attention earlier question. Question number 6. September 22nd of this year, the sun will finally arrive at the autumnal equinox. What phenomena will always occur on the equinox day, no matter where you are on the Earth? Is it that there will always be a full moon? Is that the sun will be above the horizon for just as much time as it is below the horizon? Is it all of the naked eye planets will be visible in the night sky? Is it that the Milky Way will fully encircle the horizon? Or fortune will be on your side? Now is a good time to invest. Question number 7. Katy Perry. In April of this year, Katy Perry made news by taking part in Blue Origin's public spaceflight program. How far above the surface of the Earth did Katy Perry get on that flight when she got super emotional? Was it about 5 miles, 60 miles, 250 miles, 8,000 miles, or 250,000 miles above the surface of the Earth? Question number 8. The image shown displays a notable discovery from 2025 with the James Webb Space Telescope. What is the discovery of? Is it the first direct image of an exoplanet? Is it a new moon around Uranus? Is it the oldest member of the asteroid belt? Is it a collision between two stars in the Milky Way galaxy, or is it the largest known comet in the solar system? Question number 9. Besides the sun, which star appears the brightest in the sky? And we'll say before it goes supernova. Is it Polaris, Arcturus, Proxima Centauri, Betelgeuse, or Sirius? Question number 10. The following drawing depicts a particularly rare event observable to the naked eye that was most famously observed by a young Abe Lincoln. What is the event depicting? Is it an auroral shower or an extreme version of the northern lights caused by an X-flare explosion on the sun? Is it a meteor storm or an intense version of a meteor shower caused by the Earth passing directly into the tail of a comet? Is it a cosmic fireball or a meteorite explosion in the upper atmosphere of the Earth? A lunar luminescence, sudden brightening of the moon as a result of a meteorite impact on its surface? Or is it dawn dust, the brightening of dust in the Earth's atmosphere near sunrise? All right, so what you guys are going to do now is I'm going to start cycling through these. In about 10 minutes, 15 minutes, I'm going to ask you to turn them up to the front. Don't forget, you guys got more questions. You got more questions right than wrong, which means as you're turning them in, you can get some of these mini prizes up the front. And then I'm going to go back to that QR code for you to scan it in. And hopefully now you understand the pun a little bit. If you want to donate some money, we'd appreciate it. You can decide between your favorite, either Soup or Nova. All right, so I'll go back to the QR code. You guys are supposed to laugh. Everybody laugh now. Laugh right now. All right, we'll go back to the QR code, and then I'm going to get these cycling through. And if anybody from Firefly is listening, you guys can turn on the music now for the next 10 minutes or so.
What number of questions is it?
We still got about 5 minutes or so here, but don't forget to come grab some prizes up the front for your mini game victory as well, while you're turning stuff in. And also, it seems like the music's not working, so thankfully Sahana volunteered to sing for the next 5 minutes. Nah, I'm just kidding.
Not even that.
That's what I was.
All right, we got about 3 more minutes until I'm going to ask you guys to turn those sheets in. Is there any question somebody specifically wants me to go to right now? If not, I'll just continue to cycle. But if there's a specific question, just raise your hand and I'll flash it forward to that. All right, if not, then let's go about 3 more minutes before I'm going to ask you guys to turn those sheets up to the front. Alright guys, let's get those cards turned in, and then we're going to start our next trivia game, what we call grab bag trivia, before we move into the final talk of the night. So a couple more minutes. Grab a bunch of prizes, grab a bunch of them.
They'll never feel tired.
You can retire, you can retire. It won't be a threshold.
For me, I don't know. The licenses expire. So that might be.
Yeah, you'll get some still. Yeah, I think I finished it all. Yeah, I mean, I knew it was a lot, but I didn't realize it was that much.
I put the numbers in. I wouldn't even be able to access that. I want to buy
How are you feeling about your trivia answers? You can go and get something if you want, Kristen.
I don't want to know.
You don't mind anything? They have little, like pins like those.
I don't need to throw stuff away now. It's a bookmark.
You want another book? No, they are definitely, definitely is, you. The idea is you know that there's a reason. So you don't want to beer? I'm gonna get some water. I will not be the lush tonight. You want to I will not be the lush.
You guys come to the last event or no?
All right, guys. We gotta go ahead and get going with Grab Bag Trivia. The prizes will stay after the event as well. And again, it's gonna be clear. The person that typically helps me with telescopes isn't here, so I'll be setting up the binoculars after the event for anybody that wants to look at the moon. The moon should be looking pretty spectacular tonight. It is Moon Day after all. And so don't forget to grab some prizes afterwards as well. But we're going to go ahead and start our Grab Bag Trivia. I got 5 rounds of Grab Bag Trivia. This is another way for you guys to win some of these bigger prizes up the front. And the way that it's going to work is I'm going to ask you a question just by raising your hand, first hand that I see. If you guys get it right, you have the opportunity to win that prize, right? So our first round of Grab Bag Trivia, my clicker's not working right now. Our first round of Grab Bag Trivia, let's see this. It's Know Your Astronomy. I'm going to ask you an astronomy question. Whoever gets it right first can win some of these prizes at the front. So very simply, this planet spins on its side. In the back over here.
Uranus.
Uranus is the correct answer. Round of applause. Whatever family member just won the prize. Round of applause for them. My wife will give you something. She'll let you know if you want to. And you can trade that in at the end if you want. Question number 2, round 2, astronomy anagrams. I scrambled up some astronomical word. You guys got to figure out what that word is. I'm standing in the back to help me out with this one. It'll start something like this. Any guesses? We're thinking real hard here. A little bit maybe too buzzed as the night's been going on? No. All right, let me clear it up for you guys. Maybe this will help a little bit. Actually looks something like this.
Space shuttle.
Gotta raise your hand?
Space shuttle.
Space shuttle is correct. In the back of the room, we got another winner right here. Space shuttle wins it. All right. Oh, sorry. Round 3. Round 3, I've pixelated a notable astronomical object or thing. You guys got to tell me what it is, and I'll clear it up if nobody gets it. It looks something like this. Yeah?
Good luck.
Moon landing is incorrect, unfortunately. Good guess. Other guesses?
Sun.
The moon is not yellow, notably. Yeah? I'll take one more guess. The sun is not correct, although the sun is yellow, so a better guess. I'll do one more. Ooh, we got somebody that figured it out with the first image. It is the James Webb Space Telescope, which is also yellow. Yeah, gold specifically. All right, round number 4. It's everybody's favorite game. You guys all know it. Help me out with it. It's Name That Planet. Nice. I love when that works. All right, so I've got a planet for you guys. You guys just got to figure out what that planet is. First clue, this is a fictional planet set in an animated world. Anybody guessing? Any guessers? I was hoping nobody would get it for this first clue, so let me clarify it a bit. Number 2, in the film, it is the home of hundreds of aliens, most famous for praising their sky god. Famous for praising their sky god. Any guessers here? Alright, let's clear it up a bit. With 3, an astronaut mistakenly confuses this location as his ticket home.
I don't know, but Avatar?
Say that again?
Avatar?
Avatar is not correct. Good guess for that one, though. Not Avatar. And it's not me. I'm not the astronaut that mistakenly confused the location as home. Any other guessers? All right, we're going all the way to 4. We typically only get it after 3. Let's go to 4. A famous truck from this planet frequently acts as an Easter egg across the film studio's other films. It's not Toy Story. It's Name That Planet. What's the planet? Planet. It is Pizza Planet is the correct answer to this one in the Toy Story universe. I'm Buzz Lightyear here, guys. Come on. I should have given it away. The answer to this one is absolutely Pizza Planet. The aliens praise the claw as their sky god. All right, round 5. This is Flash Trivia. Answer the following astronomy-themed question. You might typically ask, how is this different than Know Your Astronomy? It's no different than Know Your Astronomy. The question is, how do you organize a space party? In the back?
You plan it.
You plan it is absolutely correct there. Round of applause for that one. All right, so what we're going to do now is we're going to transition to our last talk of the night. Our last talk is going to be by Daphne Broski-Laing. So Daphne, if you want to come up to the front. Before I introduce you. So Daphne is a second-year graduate student in the UVA Astronomy Department. She's specifically interested in using the James Webb Space Telescope, although she wasn't able to figure that one out, the pixelated image. Using the James Webb Space Telescope to study the atmospheres of brown dwarfs and giant planets outside of our solar system. Outside of her research, she's passionate about protecting dark night skies, organizing community outreach programs for kids with UVA's Astronomy Outreach Group, Dark Skies, Bright Kids. And today, Daphne is going to be talking about a story. There once was a distant world who got swallowed by a star and lived to tell the tale. All right, so give me a moment to set up Daphne's talk before we go ahead and get going with it.
Super well done back to the table here.
No, I got the that one. What?
You got 2 out of 5 last year. See, your words,
Like the jumble, like in the newspaper, the jumble puzzle. I mean, you got to be able to.
The space thing was, the space was quick, and I was working on the second, so I might have gotten there. You were on it. So.
I wasn't.
The space was really obvious after we separated a few words. But I was still working on the second. Nicely done.
Yeah, my mom, like you know when they'll talk about the jumble puzzle in the newspaper? She's like, so you're going to sit there, you've got to be able to do it in like seconds. I mean, it's got to be that fast, you've got to be able to look at it.
Now, can we give a round of applause for Daphne?
I'm Daphne, and I'm very excited to tell you guys about what I've spent my first year in grad school studying. And if you didn't already hear it, it's going to be about a distant world who got swallowed by a star and lived to tell the tale. And now that you guys are all really drawn in by this dramatic title, I want to show you some pictures of my grandpa. His name is Fred, and he just turned 89 a couple weeks ago. Yeah, yeah, Fred. And my grandpa used to be a radio announcer, and he did the weather, and so he was kind of a television radio personality in the 60s and for around 30 years. And one of the things he did is he was a weather reporter, and he was not a meteorologist, but he was a storyteller, and back then I wasn't around, but I get the feeling that the weather reporting had a bit more character and presented personality than maybe it does now. And pretty much every day that he did the weather, he would draw a little hand-drawn cartoon like you can see up there. And we have a bunch of them hanging in his garage, but he would make those every day. And he had one thing that really stuck with him was the sunshine sticker, and you can see it in pretty much every one of these pictures. And it kind of became like a personal brand for him, but it was also, you know, a storytelling device. But anyways, he's not doing the weather anymore. But the sunshine sticker is still, you know, very close to our family. If you go out to the parking lot, you'll see two of those stickers on my car, so you'll know which one is me. But the reason I'm showing you pictures of my grandpa is because he inspired kind of the format or the aesthetics for my talk. So what I'm going to talk to you about is really cutting-edge astronomy research, and I'm going to do it by way of goofy grandpa-style cartoons. So the characters for this story that I'm telling are called companions, which is a very endearing name. And it's also, it means that they're gravitationally connected to each other, like the Earth is gravitationally connected to the sun. And first we have our host, which is this blue, the blue character here. And that is a dead star. So Sahana just talked about dead stars a lot. And this is a low mass star, and it's actually very similar to what our sun is going to look like eventually. And so it's the remnants of a dead star. And then our other character, which is really the main character for this talk, is the little purple character, and she is a brown dwarf. So I'll call her a brown dwarf or a brown dwarf companion, or in the title I call it a distant world. But one thing I can't call it is a planet, and that's because it's too massive to be a planet. So we draw a line around 13 times the mass of Jupiter, and if you get more massive than that, it's too massive to be a planet. But it behaves like a planet in some ways, and we'll talk about that more. But these are the two characters, and to give you a little bit more context, I'll show you how they compare to some of the systems, the objects in our own solar system. Aha, yes. So there's the sun. If I put it all on the screen, we wouldn't be able to see anything else. But you can see it's big, it's going way off the screen, and now Earth is just a little speck next to it. You could feel like a million Earths in the sun. And to add the biggest planet in our solar system, Jupiter, you can see it's a lot bigger than Earth, and it's a lot smaller than the sun. So you could stack 10 Earths up and down to reach the height of Jupiter. And that's the biggest planet in our solar system. It's not the biggest planet ever, but it's pretty big. But you might remember that I just said that the brown dwarf is more massive than any planet. So when I show you the brown dwarf in comparison to this planet, to Jupiter, maybe you'd be expecting the brown dwarf to be a lot bigger. But actually, it's a tiny bit smaller than Jupiter, It's about 3/4 the size of Jupiter, but the reason it's a brown dwarf is because it's got a lot more stuff packed in there. So it's 62 times more massive than Jupiter. So yeah, it's pretty packed in. And if you think that's dense, then I'll show you our white dwarf, which is about the size of Earth. But it's not a it's not a brown dwarf. It's not a planet. It's the remnants of a star, and so it's the size of Earth, and it's 530 times more massive than Jupiter. So that's a lot of stuff packed in a really tiny amount of space. So these are the kind of objects that we're looking at, and on their own, a brown dwarf and a white dwarf are pretty common. We know about a lot of them, but as a pair, like we have with our characters here, they are very rare. There's only about 15 known white dwarf, brown dwarf binaries that we know of ever. And that's because in general, we don't find brown dwarfs orbiting around stars in a very close orbit. But luckily for us, there's a couple of them, like this one here. It has a name ZTF 0038 plus 2030, but I'm not going to say it because it's a bit of a mouthful. But it's one of a few, and it's got a really rare and exciting and kind of intense history. But before I go into that too much, I will talk about what it looks like about 10 billion years ago. So in the corner, that's one of my grandpa's cartoons. But what we have here is a big compared to the brown dwarf, but actually it's the same size as our sun. And that's what this system looked like 10 billion years ago. And so this star was on the main sequence, which means it's just kind of in its normal hydrogen-burning star state. And the brown dwarf is orbiting around the star very peacefully, and everything is great. And then, 8 billion, 9 billion, 10 billion years pass, and the star starts getting a little bit grumpy. And we've seen what happens when stars get old. And you might imagine that it doesn't end so well for anything near to a star when it puffs up. And, I remember in probably middle school when I heard that the Earth might get swallowed by the sun someday. And I didn't like that idea. It's not going to be for 5 billion years, but it's still kind of unsettling to think about. And I think I knew deep down, if something gets swallowed by a star, it's probably not going to survive. That's what I thought. I didn't think anything could survive being swallowed by a star until my advisor, who's sitting in the back, told me that I'm studying an object that got swallowed by a star and survived. And so we really don't know what happens during that process because it's really hard to survive. But I've done my best to illustrate it. So what happens is our host star, which you can see the core at the very center, that's the core of the host star, and all of the outer layers puff up and they get big enough that it swallows the brown dwarf. And when this happens, the brown dwarf still wants to keep doing what it was doing. Newton's first law, an object in motion wants to stay in motion, so the brown dwarf in orbit wants to stay in orbit. And so it keeps trying to orbit around the core of the host, but it's now experiencing friction from the envelope. The envelope is all of this material that came out from the outer layers of the star, and so that causes the brown dwarf to spiral inwards towards the center. And if that were me, I would be very stressed about the whole situation. I would be anxious, and I would want to turn the heat down because it doesn't sound super pleasant to be inside of a star. But luckily for the brown dwarf, it didn't stay in there forever. And so now what we have is our white dwarf, brown dwarf binary pair. And what we're left with is a brown dwarf in a really short orbit around a white dwarf. And when I say short, I mean, we on Earth, we're orbiting our sun every 365 days, and this brown dwarf is orbiting its host in 10 hours. So that's intense. That's shorter than I would have Yeah, shorter than I would have expected. And that's good for observing because it's easier to convince James Webb Telescope to look at something for 10 hours instead of 2 days or a week. So, it's not only in a short orbit, it's in a short, tidally locked orbit, which is important because there's other planets that we know of that are entirely locked orbits. And those are called hot Jupiters and warm Jupiters. And they're exoplanets that are in short orbits around their star, kind of like this. And when I say it's tidally locked, I mean that we have a permanent day side, which is the side that's pointing towards the star. And there's always the other side in shadows, and it never changes. So, this is a PDF, so the animation doesn't work. But you can imagine that this planet right here is moving around the host star, but as it's moving, the day side is always pointing in towards its host. So that's what it means to be tidally locked. And in general, even though this brown dwarf isn't a planet, this fact makes it a really important way that we can probe the atmospheres of tidally locked, irradiated atmospheres. And we can understand it in a lot more detail than we can with more typical planets because of a couple things I don't really have time to get into, but these pairs are very rare, but they're really advantageous to observe. And so, kind of with this combined force of the fact that we have a really cool rarity, and we also have highly relevant atmospheric behaviors of this brown dwarf, that makes it a really compelling target to observe. And so that's what we did, and now James Webb, as of a couple months ago, had finished observing 5 white dwarf, brown dwarf binaries out of around 15 that we know of. So that's a pretty good number, and we're going to hopefully bring that number up and observe as many as we can. But this is just showing you the tidally locked nature. That's fine. But these observations allow us to answer a couple really exciting questions. So we can look at the overall structure and behavior of the atmosphere. So we can see how the irradiation from the white dwarf impacts the atmospheric structure and the circulation across the atmosphere. And we can also try to understand the formation history of this system because we don't know a lot about comet envelope evolution. And so we can try to understand how that period when the brown dwarf was engulfed might impact its chemistry and its temperature. The kinds of observations that we have to understand more about this brown dwarf are called phase curve observations. So that means that we observe this brown dwarf throughout an entire orbit, and an entire rotation, more importantly. And again, the animations are not animating, but what we have is, if you were to look at our system from the top down, you would see the brown dwarf going in a circle around the host. But in reality, this system is edge-on, so we see the brown dwarf go kind of back and forth, and at some point it crosses in front of the white dwarf, and then it eventually passes behind it too. And during this time, we observe how the brightness of the brown dwarf changes with time. And the first thing you notice is that there's a really big drop in brightness right here, and that corresponds to the moment when the brown dwarf crosses in front of the white dwarf. And when that happens, we lose a lot of light because the white dwarf is really bright. But there's another variation that we see if we zoom in a little bit further and we ignore that time during the eclipse. And we see how the brightness is changing more steadily, and it's a smaller scale, but this is kind of the important variations that we're observing, because this is showing us how the brightness is changing when we're seeing different faces of the brown dwarf. So during the peak, this is when the day side is facing us, and here at the trough is when the night side is facing us. And so encoded in this data is a lot of information about like the temperature difference between the day and the night side, and how the energy is transported across the atmosphere. But this is not all of the information we get from our observations. We actually go, we get a little bit more in depth. So for every one of these points that we observe, we're not just getting the total light, we're actually splitting that light into a spectrum. And so for every point, we get a spectrum, and that's what Pink Floyd shows on their album cover. Yeah, we got a Pink Floyd fan. But the prism is exactly what we're doing. We're putting our light through a prism and splitting it up. And for the album cover, you see the rainbow, and we're using James Webb, which does not look at visible light. It's using infrared, but the same thing happens. And so each down here, this shows the wavelength, and it's kind of like the color, even though it's not visible. And we can see how this spectrum changes as the brown dwarf rotates. And this is important because this tells us even more detailed information about how the temperature is changing as the brown dwarf rotates, and how the chemistry is changing. And so what we did is we can look at the spectra at different phases. So you can see here's the day side, and that corresponds to the yellow spectrum up at the top, and they're all stacked. And then at the night side, we have, you can see that it's darker or dimmer in some wavelengths, but in some wavelengths, it actually stays pretty constant throughout the entire orbit. So that tells us important details about the atmosphere too. So this data set is really rich. It has a lot of information packed into it about the atmosphere in 3 dimensions, which is important because it's really hard to study an atmosphere of a planet, for example, in 3 dimensions, because we're looking at a point source. When you point at James Webb at this, you don't see an object orbiting another object like this. You see one dot, and you see the light changing. And from that, we're able to learn about the 3D properties of the atmosphere, which is really amazing. And these specific objects make it possible to learn a lot of really detailed information about the 3D structure, way more than you can learn with a typical exoplanet for a lot of different reasons. But some of the exciting things that we're starting to find, and this is still, an ongoing work. We've had the data for maybe 7 months now, and there's a lot more that we can do with it, but we're starting to learn about things like the circulation from the day side to the night side. So we're finding that the energy that's coming in to the day side from the white dwarf is not being transported very efficiently over to the night side. So only about 8% of that energy is getting transported across the atmosphere. And we are also able to see evidence that there may be a hotspot concentrated right at the point where the brown dwarf is facing directly at the white dwarf. And that kind of makes sense if we have low energy transport efficiency, that there's a lot of energy that's trapped right there facing the white dwarf and getting bombarded with the radiation. Then we're also looking at how the chemistry of the atmosphere is changing as we're seeing the different phases, and we're finding that actually for this object, it appears that the chemistry is saying the abundances of the molecules that we're looking at are staying pretty constant, even in the varying irradiation levels that the brown dwarf receives. So that tells us about what kind of chemistry is shaping the atmosphere. And we're finding how the temperature changes both as a function of its height. So we can see what the temperature looks like deep in the atmosphere and higher up, and also how it changes from the day side to the night side. And the reasons that these findings and this observing program in general is really compelling, well, a few of the reasons are because, firstly, these observations allow us to make the most precise map of any irradiated substellar object ever. And by substellar, I mean an object smaller than a star. So this is really huge. It's a really high quality data set that has a lot of information encoded in it. So we want to spend a lot of time, getting the most out of it that we can. And it's also allowing us to learn about the end stages of planetary systems, which it's becoming more possible now that we have James Webb, but it's a very unknown field right now. So we get to start probing later in the lifetimes of stellar systems and substellar companions. And we can apply these findings for other exoplanets. So like I said, white dwarf, brown dwarf binary pairs themselves are really rare, but the knowledge that we learn from them can be applicable to the exoplanet population more broadly, which is really important and will be an exciting step that we can take in the future. So with that, I'll put back on our characters for tonight and I'll take any questions.
All right, we got some time for questions for Daphne. So does anybody have any questions to start us off? And I'll come running over with the microphone. Right here, yeah.
Hello, how are you? So I've got a super weird question for you, okay? Okay. So you mentioned that you're getting kind of a sense from the spectrographs of the chemical structure of the atmospheres of these brown dwarfs, right? So the other day, I don't know if are you familiar with Mineral Cup?
No.
So there's this geology game that's going on right now where geologists on social media pit different minerals against each other and then they vote to see who wins.
I love that.
And there was one the other day, there was perovskite, and the thing that they were trying to use to get people to vote for perovskite was that brown dwarf atmospheres rain perovskite. Have you ever heard about that? And if not, what's in their atmospheres? How would you characterize what's going on in the atmospheres of brown?
Well, I've heard about perovskite being in brown dwarf atmospheres, but not about them raining it, so that's cool. And I'll have to look into it, yeah.
Daphne, quick question. For those of us who don't know, who could be anyone here, what is perovskite? Certainly not me, but for everybody else that's sitting there. I retract my question.
That'll be a good piece of homework we can all do after. Unless someone else. But I know, I don't know for this specific system, but what we do know is in the atmosphere and what we're seeing kind of with the first pass is we're looking at the carbon monoxide and carbon dioxide and methane and water, and so we're seeing absorption features there, and but yeah, there's more information encoded in this data, and we're still kind of starting to get through it. So it's also a bit of a work in progress.
You got a question in the back here as well?
Yeah, I'm struggling with why the center of the mass of the atmosphere would have a higher temperature gradient. You said it was logical, but it wasn't logical to me.
Wait, can you repeat that?
Yeah.
So I think it's getting at, why is the center of the brown dwarf hotter than the outer atmosphere of the brown dwarf?
Oh, okay. Well, I don't know quite where I brought that in. But anyways, one thing that's interesting about brown dwarfs as compared to other planets is that the amount of heat in the brown dwarf is partially coming from the white dwarf, but then also the brown dwarf itself has internal heat that comes from the formation. And actually, this gets to another piece of information that we can learn about how what happened when this system was engulfed, is that we are wondering if the brown dwarf actually gets even hotter when it was engulfed by the star. And maybe surprisingly to you, and maybe surprisingly to me, is from our first look at what we've done so far, and this is also a work in progress, we aren't actually seeing evidence that now, which is 400 million years later, that the brown dwarf has extra heat. So maybe in this system, it didn't get as much heat as I might have expected, imagining a brown dwarf inside of a star. But yeah, so the brown dwarf has heat in the center of the system.
Right over. Question over here.
So I thought a brown dwarf was a star, a very, very low mass star, and it was fusing hydrogen at some point, no?
No, so a brown dwarf is right in between, so it's not massive enough to be fusing hydrogen.
So Trappist-Lowe, I thought Trappist-Lowe was a brown dwarf.
No, it might be an M dwarf. There are, and which would be a low mass star. But yeah, there's lots of astronomical terms that use. There's white dwarf, brown dwarf, M dwarf, and yeah.
Astronomers suck with names, basically.
So you said the atmosphere, like where the hot spot is, it's like the same as throughout the dwarf, right?
So, well, it's hotter. There's like a concentrated area that's hotter, but in terms of the chemistry, we're seeing the same molecules as we do on the night side.
Yes. So then, like, would that imply anything for the molecules that are in the atmosphere, like anything about how they might handle different radiation levels or anything of that sort?
Yeah. So, if you'll believe it, this object with its 10-hour orbit is actually the longest orbit out of all of the white dwarf, brown dwarf binary pairs that we're going to be looking at. So in comparison, we're going to look at some other objects that are receiving a lot more radiation, and we would expect that the irradiation in those objects is going to dissociate molecules more. And yeah, so that's definitely something that is important to think about.
And I think we've got time for maybe one more question. So I'll run up the front here.
Do we know what causes an object like a brown dwarf or the moon to assume the tidal orbit?
So in this case, we don't actually know we don't know in where it loses angular momentum that causes the system to reach that state faster, and eventually, like it takes time for a system to become tidally locked, but being engulfed made it easier to reach that state. Yeah.
All right, cool. Well, let's give another round of applause for Daphne. And if you guys have one of the things I wanted to say, if you guys do have any questions after the event ends, feel free to ask Daphne, Sahana, myself, any of the other astronomers some lingering questions you have. That's one of the cool things about these events, right? You have the experts at your fingertips, sort of take advantage of that expertise for any lingering questions that you have. All right, so what we're going to do now is we're going to transition then to revealing the trivia winners, and then I'm going to go about setting up binoculars afterwards. So give me a moment to set that up. Chat with your family members for about 30 seconds or so. was great. You guys had a lot less arguments than I do with my family members, so I appreciate that. Nice. All right, so let's go ahead and reveal who the winners were. And just so you know, there was one team that got 10 out of 10 correct. They will be the ultimate winners. We'll see if there's other winners as well. So, question number 1. Which of the following does not find its origin involving astronomical objects in the sky? That is the minute. Month is the more appropriately called a moon. It's the amount of time from new moon to new moon. And stands for before the meridian. When the sun is before this thing called the meridian. There were 7 wandering stars in the sky. That's why each day of the week is named after one of those wandering stars. Today is the moon's day. Tomorrow will be Mars's day. And then the year, of course, is how long it takes the Earth to revolve around the sun. Question number 2, where does the name supernova come from? Nova is Latin for new, specifically a new star. It's when a new star appeared in the sky. All right, question number 3, what was never used or proposed as the name of a planet or large object in our solar system? That is Jason in the Argonauts, was never used as a name. George's star was the original name for Uranus, which is, good instincts. If you're an astronomer and you want funding, name it after the leader of your country. They'll give you a lot more money if you do that. But we named it after the Roman sky god instead. Vulcan was the original name of this mysterious star that we thought was maybe at the same distance as the Earth, but on the other side of the sun that we couldn't see. No, it doesn't actually exist. Makemake is a dwarf planet in the solar system, and Juno was the original 9th planet of the solar system, but is now an object that we call an asteroid. Question number 4. When was the first planet outside of our solar system discovered? That was in 1992, around a dead star called a pulsar, where we did not expect there to be any planets. The next discovery was also of a planet that we didn't think shouldn't have existed. Goes to show you how much we knew. We learned a lot about astronomy as a result of that. Question number 5. Which of the following solar system planets has the longest day? It's the most spherical planet, which is Venus. Venus takes 243 days to spin once. It actually takes a shorter amount of time for it to go around the sun once. Venus's day is longer than its year. Question number 6. What always occurs on the equinox? Equinox means equal night. It is when the sun is above the horizon.